Pluto, a distant and mysterious dwarf planet that was once part of our solar system's family of planets, has re-emerged in the scientific debate with surprising revelations from leading astrophysicists Neil deGrasse Tyson and Michio Kaku. These experts suggest that this icy world is on a possible collision course with Neptune. But how could this happen, and what would be the consequences of such a massive event? Are we witnessing a rare astronomical phenomenon, or is there more to this impending cosmic collision? Pluto, reduced to a dwarf planet in part by its own orbit, remains an exciting and exploratory astronomical community. According to recent predictions, Pluto's orbit is dangerously close to that of Neptune. Tyson and Kaku both raise a red flag about a possible dangerous collision between these two celestial bodies that could pose an enormous threat to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes 248 years to complete one orbit, meaning it hasn't even made one complete revolution since its discovery in 1930. But the plot doesn't end there. Pluto's path is marked by its highly elliptical shape, which is very different from the nearly circular orbit of the major planets. What makes Pluto's orbit even more special is its inclination, which is at an angle of 17 degrees to the plane of the ecliptic. This steep inclination is in sharp contrast to the orbits of other planets. One of the most interesting aspects of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto is actually closer to the Sun than Neptune, challenging what we might expect from their position in the solar system. This leads to a natural question. Why didn't Pluto collide with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. At first, astronomers struggled to understand its unique trajectory. Unlike planets whose orbits are relatively close to the ecliptic plane, Pluto's path was distinguished by its steep slope and elliptical shape. The mystery deepened after it was realized that the orbit of Pluto actually exceeds that of Neptune. The stability of Pluto's orbit in the midst of their complexities is a testament to the complexity of space mechanics. The three-body problem in space, figuring out how Pluto, Neptune, and the Sun move and affect each other with their gravity, is a major challenge. Pluto's orbit is technically chaotic, and small deviations from initial conditions add up to significant differences over millions of years. However, these unique features of Pluto's orbit are found to maintain stability for incredibly long periods of time, effectively keeping chaos at bay. Numerical simulations in the late 1980s showed this stability despite the chaotic nature of the orbit. Recent computer tests have helped us understand how large planets like Neptune, Jupiter, and Saturn affect Pluto's path around the Sun. Jupiter's gravity alone is strong enough to keep Pluto on a stable path for a very long time, even billions of years. These phenomena are necessary to maintain order and predictability of movement in space. Without these mechanisms, the solar system as we know it would be a place of much greater chaos and unpredictability. Pluto's orbit is a remarkable example of celestial mechanics, showing both stability and chaos in our solar system. The unique features of its orbit, influenced by the gravitational pull of neighboring planets, especially Neptune, reveal the complex and dynamic nature of the cosmos. Predicting cosmic events, especially when they involve chaotic orbits like Pluto, presents significant challenges. The inherent unpredictability of these systems means that long-term forecasts are often fraught with uncertainty. Although numerical simulations provide a powerful tool for understanding and predicting the future trajectories of celestial bodies, they also highlight the limits of our predictive power. Why are mainstream astrophysicists now worried about a possible collision between Pluto and Neptune, despite all the complex forces trying to prevent such an event? Tyson and Kaku, both prominent figures in astrophysics, expressed concern about a possible collision. If Pluto and Neptune were to collide, it would be a rare and catastrophic event in our solar system. The collision would release an enormous amount of energy that would likely shatter Pluto due to its smaller size and icy composition. Debris from the collision could spread across the solar system, potentially posing a threat to other planets and their moons. For Neptune, such an impact could change its atmosphere and possibly its orbit, depending on the specifics of the impact. Michio Kaku, a renowned theoretical physicist known for his work in string theory, brings a unique perspective to this discussion. His insights into the future of space exploration and the interplay of celestial mechanics and theoretical physics provide deep insights into the mysteries of space phenomena such as the orbit of Pluto. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies, such as Pluto, can provide important insights for future space missions. This knowledge can help navigate the solar system more efficiently, anticipate potential threats, and even plan missions to the outer reaches of our solar system and beyond. Lessons learned from the study of Pluto's orbit can be applied to the study of other celestial bodies, providing a blueprint for how we can approach and understand distant worlds. When it comes to planetary physics, celestial mechanics and theoretical physics are closely related. The movements and interactions of the planets, such as the gravitational dance between Pluto and Neptune, are related to basic principles of physics. If Pluto and Neptune collide, it would be a monumental event in astrophysics, providing a unique observational opportunity that could potentially be linked to string theory. String theory, a theoretical framework in which the point-like particles of particle physics are replaced by one-dimensional strings, aims to describe the fundamental forces and matter of the universe. The collision could produce extreme energy and gravitational conditions, potentially creating scenarios where the effects predicted by string theory could become observable. For example, the high-energy effect can provide insight into the behavior of fundamental particles and forces under extreme conditions, a central interest in string theory. Even if the direct impact on Earth were negligible due to our distance from the outer solar system, the scientific implications of such an event could be profound, potentially advancing our understanding of the fundamental nature of the universe as described in string theory and other fields. Of theoretical physics, Pluto's enigmatic dance around the Sun continues to fascinate scientists and enthusiasts alike, providing a window into the complexity of celestial mechanics. Although its classification as a dwarf planet has sparked debate and changed our understanding of planetary bodies, recent revelations about its orbit have reignited interest in its role in the solar system. Tyson and Kaku raised concerns about a possible collision between Pluto and Neptune, shedding light on the complex dynamics of our cosmic neighborhood. Their warnings emphasize the importance of understanding the gravitational interactions and orbital mechanics that govern the motions of celestial bodies. Characterized by its eccentricity and steep inclination, Pluto's orbit defies conventional expectations and challenges our understanding of planetary motion. Unlike the relatively circular orbits of its neighboring planets, Pluto's path follows a unique trajectory that intersects Neptune's orbit at points that go around the Sun.
The gravitational influence of other planets, especially Neptune, plays a crucial role in shaping Pluto's orbit and maintaining its stability over millennia, despite the chaotic nature of its trajectory. Numerical simulations have revealed the underlying patterns and mechanisms that help regulate Pluto's motion and avoid catastrophic collisions with neighboring celestial bodies. The three-body problem in space, which includes Pluto, Neptune, and the Sun, describes the complex interaction of gravitational forces and orbital dynamics that govern the behavior of celestial bodies. Understanding this complex system requires sophisticated mathematical models and computer simulations that provide valuable information about the long-term evolution of planetary orbits. Pluto's position as a dwarf planet has sparked debate about the criteria for planetary classification and the diversity of celestial bodies in the solar system. Although its small size and distant orbits separate it from the traditional definition of a planet, Pluto's importance as a celestial body continues to attract scientific research and public interest. The study of Pluto's orbit extends beyond the boundaries of our solar system, providing insights into broader astrophysical phenomena and fundamental laws of physics. Many other predicted potential disasters underscore the ever-evolving and dynamic nature of space. Understanding these patterns will help us learn more about how the planets move through space, especially when they are very close. Rogue planets drifting through starless space add another element of unpredictability. Those planets that were once part of the star system are thrown off by gravitational perturbations or other celestial events. Over time, they drift into space, traveling long distances and possibly reaching regions far from where they are on their lonely journey. Rogue planets may cross paths with other star systems. If one of these wandering planets crosses another solar system, there is a small chance of colliding with a planet in that system. However, space is incredibly vast and mostly empty, so the chances of a rogue planet directly hitting another planet are extremely low. The range of interstellar distances and the relative rarity of planets in open space act as buffers against repeated collisions. Pluto's enigmatic dance around the Sun continues to fascinate scientists and enthusiasts alike, providing a window into the complexity of celestial mechanics. Although its classification as a dwarf planet has sparked debate and changed our understanding of planetary bodies, recent revelations about its orbit have reignited interest in its role in the solar system. Tyson and Kaku raised concerns about a possible collision between Pluto and Neptune, shedding light on the complex dynamics of our cosmic neighborhood. Their warnings emphasize the importance of understanding the gravitational interactions and orbital mechanics that govern the motions of celestial bodies. The study of Pluto's orbit extends beyond the boundaries of our solar system and provides insight into broader astrophysical phenomena and the fundamental laws of physics. Understanding the patterns of celestial bodies helps us learn more about how the planets move through space, especially when they are very close. Rogue planets drifting through starless space add another element of unpredictability, emphasizing the dynamic and ever-evolving nature of the cosmos.